All right, for the buoyancy experiment, we're going to be looking at the buoyancy of wood in water, and there are essentially two parts to it. So we've gone over the theory in class where the buoyant force is equal to the weight of displaced water, and that means some of the, when something is floating, some of its volume will be above water and some of it will be below. So we're going to have two different but related experiments here. The first one, you're going to take different species of wood and look at how they're floating in water, and then in the second part, take one of those species of wood and see how it floats in a concentration of salt. So let's bring up the data that you will need. For the different wood blocks, there are 5 blocks, blocks A through E, and their dimensions and mass are listed here in this document. So you'll need to know the dimensions to calculate the volume, and then the mass with the volume can give you the density of the block of wood, which will allow you to make a theoretical prediction for how much it should float or how well it should float. The before and after pictures are here. So this is before the blocks are added and after the blocks are added, and you can see that they float to different degrees depending on species. So by comparing the water level before and after, you can see a height change and then use that to calculate a volume change. The volume change is the volume of water that has been displaced by the block. Now, for the analysis, you're going to put the data into here. So we have the mass of the blocks, the length, width, and height of the blocks in millimeters go in here. The spreadsheet will automatically calculate the volume in cubic centimeters and produce a theoretical prediction for what volume of water is displaced, and also something which I call the buoyancy parameter. So if you come back into the lab handout, the original lab handout, the buoyancy parameter is defined here, and it's basically a way of saying what percentage of the block is above water. So something that's more buoyant would have a higher percentage above water, and so the buoyancy parameter measures how buoyant it is. How a higher number means more buoyant. So the spreadsheet will calculate that for you automatically, and you'll have the buoyancy parameter theoretically here. Then you can use the picture to find the height difference in the water using the ruler for scale, and plug those height changes here on the screen. So you're looking at the picture on the screen, so you put the height change on the screen. So you'll need a ruler. It's the only tool you'll need is a ruler to measure the height difference between here and here, and then an estimate of what your uncertainty is in those values. But we need the real height change, and to get the real height change you need to do a scale conversion. So this is a basically 30 centimeter ruler, and so that's its real measurement. You'll also need to measure the ruler on the screen, and then a scale factor will be calculated here, and the real height differences will show up here with the appropriate uncertainty based on these uncertainties. So what are you inputting? You're inputting the mass, length, width, height of each block, the height change as measured on your screen, and the ruler length as measured on the screen, along with the uncertainties in these heights. One point of caution, once you start measuring the heights, you want to keep the image the same size. So if you change, like you blow up, try to zoom in, that's going to mess with your scale. So you need to keep the image at one size while you make all of these measurements in order to be consistent. Now, to go into the theory, there are a couple other things you'll need. One is the temperature, and the temperature in the water was measured to be 18.5 degrees. And if you go to this site, that will allow you to estimate what the density of water should be. Then the last thing is the radius of the container, which is used to calculate volume. And the interior diameter of the container was measured with calipers to be 59.5 millimeters. So you can use that to find the radius. And I think that's all you need to enter into this spreadsheet, and you should see that the blocks vary in their amount of buoyancy, with the most buoyant being block A, and I think the least buoyant is block E. All right, so that's the first part of the experiment. In the second part of the experiment, you're looking at salinity. And to measure salinity, you need to make a salt solution. If you click the link in this document, it'll take you to a video which shows me making the salt solution. And so you can see that process there. And in that video, you'll see that the mass of water used was 151 grams, and the mass of salt used was 6 grams. So you can use that information to calculate the concentration of salt and ultimately the density of the water, the density of the salt water. I did this one a little bit differently because I forgot to include the ruler beforehand in the images as I was taking them. So instead, I measured the height of the containers and then took an image of the ruler and blew it up and calibrated it so that the height of the ruler was matched the height of the containers in real life. So you can actually read the height change by using the ruler here. So measure the height at this level, compare it to the height of the water at this level, and that's your height change in water. On the spreadsheet for the salinity experiment, you're putting in the mass of the block, volume of the block, and then the freshwater data. So all of this data is the same as row E over here. So mass, volume of the block, and then your screen measurements from the first part. And then over here you enter the new data for the saltwater solution. So the change in height in this image and your uncertainty in that height. So this one, it goes really quickly because you already have all of this data here collected. The temperature is the same temperature of water from the beginning. Then the density will be the same as before. It's the same container, so the same radius. The mass of water will be this number, and the mass of salt will be this number. So the concentration of salt will calculate automatically for you in the density of salt, and you should see a noticeable difference between the buoyancy in salt water and in fresh water. Okay, and that's it for the data collection. From there, you're answering the two questions that are in the lab. How do the wood species compare based on your results, and then how does the salinity affect the buoyancy based on your results?